Welcome to this lecture series in real analysis. In this lecture, we'll discuss the notion of accumulation points of a set. And let us recall what we need. Well, all we need is the basics. And particularly, we'll need the notion of a neighborhood. It's hardly anything to recall. If you are given a real number x, a neighborhood of x is just any open set containing x. That's it. And of course, we'll use some basic things that we have learned so far, but no point recalling them here. So let's proceed. Here are some problems for practice. And now let us get started. So first, let us define the meaning of a deleted neighborhood of a point. So fix a real number x. A deleted neighborhood of x is any set of the form u minus x, where u is a neighborhood of x. So let me explain pictorially. Suppose we have a point x on the real line. You take a neighborhood of the point x, call it u, and remove the point x from it. So just delete the point x from it. What remains is that, and this is called a deleted neighborhood of x. Hardly a difficult concept. It's just useful in terms of exposition, not a deep concept. Let us also define the notion of the delta neighborhood of a point. This might also help at in some particular context. So fix a positive real number delta. Then the delta neighborhood of x is just the following set. This union that. What is this? So pictorially you have, sorry about this. So you have the set of real numbers. Let's say x is here. So this thing is nothing but the thing that I'm going to shade. So it's that union this part. So this is x minus delta, that is x plus delta. And the union of these two intervals is that this is the delta deleted neighborhood of x. Basically, you take the delta neighborhood of x and remove the point x from it. That's it. Nothing interesting going on. Let's proceed. So we'll define the notion of an accumulation point, and unfortunately I've written a lot of things here. Let me erase it. Okay. So fix a subset S of reals and let x naught, let me remove the naught. Suppose x is an arbitrary real number. So we are not asking that little x be in S or anything. S is just an arbitrary non-empty set and x is a real number. We say that x is an accumulation point of S if what happens? If for each deleted neighborhood D of x, we have D intersection S is not empty. So we'll see examples to understand the concept, but let's try to verbally flesh it out a little bit. We say that x is an accumulation point of S if in every deleted neighborhood of x, there is a point of S. So in some sense, you could say that S is not leaving x alone. That's heuristically what you can say. So let's try to foster our understanding using an example. So here the set is all the integers, and we can depict them via diagram. So let's say, again this yellow thing comes about. So let's say this is our real line. And we have the integers, the 0, then we have 1, 2, and so on. All right. So these things are precisely the elements of S. Let's argue that 0 is not an accumulation point of S. I mean, we are going to argue that no point is an accumulation point. In particular, let us argue that 0 is not an accumulation point of S. So to do that, we need to find a deleted neighborhood around 0 which misses S entirely. Can we find it? Of course we can find it. Just consider this deleted neighborhood. The half deleted neighborhood of 0 is one such deleted neighborhood which misses S entirely. And yes, the points of S kind of leave 0 alone. 0 is kind of happily sitting in its own space. If you forget 0 for the moment, the other points of S, they are far away from 0. Of course, 0 is already in S, so you could say S is infinitely close to 0 because 0 itself is in S. But if you forget about 0 and just think about the other points of S, they are not bothering 0 too much. So 0 is not an accumulation point. Similarly, none of these things are accumulation points. And similarly, no real number is an accumulation point of S. You pick any real number, it is left alone by S. The other points are far away. So the set of accumulation points of S is empty. Okay. So that was nice. What about this very simple example? So here, let me again draw a picture. I don't want to make a crooked line. Oops. Okay. And here we have our interval. This is A and that is B. Now, it should be clear to you that these points are not accumulation points of the set S. And by these points, I mean the points which are strictly greater than B. And these are the points which are strictly greater than A. Why? Because if you pick any such point, there is not just a deleted neighborhood around it that misses S. There is a neighborhood around it that misses S. Right? An entire neighborhood misses S, and hence this is not an accumulation point. So the only candidates for accumulation points are the things which are in this closed interval AB. What about B? Is B an accumulation point of S? Well, whenever you make a deleted neighborhood around B, you are forced to consider some of the points which are on the left of B in that deleted neighborhood. And these points will creep in. So any deleted neighborhood of B intersects the set S. It cannot miss S clearly. So B is an accumulation point. Similarly, A is an accumulation point. And similarly, anything in between is also an accumulation point. If you make a deleted neighborhood around this point, it will contain a lot of points from S. So this line is not horizontal, and that is kind of bothering me. Is it horizontal? It is horizontal, thank God. Yeah. So where was I? So I have argued that the set of accumulation points of S is precisely this set. This closed interval. Okay. Now lastly, a more interesting example. A little hard to explain, but it's not difficult at all. So let me draw what this set is. We have the set. Okay, so let's kind of try to draw it. Maybe I'll include 0 in it. Doesn't matter. I'll include 0 in it just for convenience. So 0 is here and 1 is, let's say, here. Then we have half. We have 1/3, 1/4, and so on. What are the accumulation points of this guy? Well, clearly, if you choose anything which is away from this set, that's not going to be an accumulation point of S. That's clear from the picture, but let me just say why 2 is not an accumulation point, because it's not an accumulation point simply because as soon as you choose, or rather, I should say, there is a whole neighborhood around 2 that is missed by S, and hence 2 is not an accumulation point. In fact, as soon as you have a closed subset of reals, everything outside that closed subset cannot be an accumulation point of S. The set of accumulation points of S is contained in the closure of S. That's something that if you followed the lectures, the previous lectures, you should be able to see, but we will prove something effectively. Very soon we'll prove that. So anyway, anything outside S cannot be an accumulation point of S. What about the things which are in S? What about this guy? Well, again, if you take this small deleted neighborhood, that misses every point of S. So 1 is not an accumulation point. Similarly, half is not an accumulation point because you'll have to squint your eyes and choose a smaller deleted neighborhood, but you can choose such a neighborhood. That also misses every point of S. Similarly for this, similarly for that. But this guy doesn't have that luxury. No matter what deleted neighborhood you choose around that point, you will trap in points from this part, simply because this converges to 0 as n increases. So the only accumulation point of S is the real number 0. Okay. So I hope this concept is clear, the concept of accumulation point. And here is a remark. An accumulation point of S may or may not lie in S. So here, for instance, A is an accumulation point of this guy, of the open interval S, and it does not lie in S. The point A is not in S. But here, 0 is a point in S and is also an accumulation point of S. So an accumulation point of a set may or may not lie in the set. Okay, all right. Now, I guess, we are far from over. Let's try to understand this notion a little bit better. So fix any non-empty subset of reals. It is non-empty, I'm not writing that. And fix an x arbitrary, a real number x arbitrary. Then these two statements are equivalent. What is the first one? The first one is that x is an accumulation point of S. And the second one is somewhat bizarre looking thing. All we are saying is first you take out x from S and then take the closure. So I should have mentioned in the recall that you should be familiar with the notion of closure. If you're not, then you can go back to the videos or maybe Google around. Very important notion. So x is an accumulation point of S if and only if x satisfies this. So let's prove it. And I strongly recommend you to first try to prove this yourself before you look at what I'm going to discuss. So assume 1, want to show 2. And to show 2, what do we need to do? What do we need to do to show that something is in the closure of something? We need to show that whenever we choose a neighborhood of x, it intersects that guy. So let U be a neighborhood of x. Need to show that U intersects the punctured set S. Need to show this. But, well, by 1, meaning that since x is an accumulation point of S, we know that this deleted neighborhood, this is a deleted neighborhood of x, and hence this intersects S in a non-empty set, which is same as saying that this is the case. So we have proven what we wanted to show, and therefore 2 holds. Now assume 2. We want to show that x is an accumulation point of S. What do we need to do? Fix an arbitrary or choose an arbitrary neighborhood of x. And what do we need to do? We need to show that this deleted neighborhood intersects S. But again, this is just exactly the reversal of the previous argument. But since 2 holds, we know that any neighborhood of x will intersect this guy we know that U intersection this thing is non-empty. But that is exactly the same as saying that the punctured U intersection S is non-empty. So that's it. That proves one, and we have shown this. This helps. This is a very simple deduction, but it helps. When we think about accumulation points, remembering this is a good idea. Okay, let's proceed. So what about dense sets? This is just a special example. Clearly an exercise. You should pause the video and solve these lemmas before I give you the proofs. So fix a dense subset of the reals and pick X arbitrarily. Then this is also a dense set. This has nothing to do with this lecture. This is really an exercise. Perhaps let me prove it, because I don't want to leave this out. So why is puncturing a dense set also leading to a dense set? Suppose not. Assume on the contrary that this guy is not dense in R. Then by definition, then there is an open set U such that non-empty open set, I mean, so let me write non-empty, such that U intersection this punctured thing is empty. What is happening? If this is not dense, it should miss an open set. It should miss a non-empty open set. That's exactly what we have written. Just looks complicated. Okay. But then, this is equivalent to this intersection A being empty. But what about this guy? What about that? That is also an open set. And a non-empty one at that. If you take a non-empty open set and puncture it, you are going to get a non-empty open set. So what I'm using is that this is a non-empty open set. Now we have a non-empty open set whose intersection with A is empty. That contradicts the fact that A is dense in R. And this contradiction establishes that this must also be dense, because we had assumed otherwise and ended up with a contradiction. Okay, so puncturing a dense set gives a dense set. And as a corollary, whenever we have a dense subset of reals, each real number is an accumulation point of A. Just use the previous criterion. We need to show that X is an accumulation point of A. So what we need to do is that X is in the closure of that guy. But since this is dense, we just showed it. If A is dense, then this is dense. And hence its closure is everything. That's precisely what density means. So that's it. So if you have a dense set, everything is an accumulation point. In particular, the accumulation point of the set of rationals is everything, is all real numbers. Okay. Now we have a cousin or a kind of a antithesis notion of accumulation points. So what is it? Fix some non-empty subset of reals. We have a non-empty subset of reals and some element of S. This is not just some arbitrary real number. This is an element of S. We say that this is isolated in S if there is a neighborhood of X, neighborhood U of X, let's say, neighborhood U of X such that U intersection S is just this singleton. Let's try to understand what I just wrote. You should pause the video and read it and think about it, but let me get to the example. So we have the set of integers. Hopefully this line is horizontal. It is. Let's mark out the set S. So I want to illustrate that every point of S is isolated in S. Okay. So you pick the point 0, let's say. We want to show that 0 is isolated in the set of integers. And by definition, all we want to show is that there is a neighborhood around 0 such that the only point of S that is there in this neighborhood is the real number 0. And that is true because if you take the half neighborhood, that only intersects S in 0, nothing else. And this does justice to the phraseology. It is kind of sitting lonely in the set S. It is isolated from all the other things. The other things are not coming closer and closer to it. So it's kind of a dual notion to the notion of accumulation. Okay, what about this example? Here, let me leave this as an exercise. So here, so 1 by n is isolated in S for each n, but 0 is not isolated. Prove this. Take this as an exercise. Okay. And since it is a dual notion, or we feel in our guts that it is a dual notion, let's just make that precise. Take any non-empty subset of reals and fix a real number arbitrarily. Then the following two statements are equivalent. The first is that x is isolated in S. So this is wrongly written. I wanted to say that x is in S. So the first statement is that x is isolated in S. And the second is that x is not an accumulation point of S. And this is immediate from the definitions. So proof, obvious or clear, which just means that you take that as an exercise. It's a one-line argument. Okay. Now we'll prove something very nice. Suppose we have an uncountable subset of reals. Then it has an accumulation point in itself. I mean, I could have stopped the statement here and still it would be an interesting one. But it is more interesting this way. Not just that this has an accumulation point, but that it has an accumulation point in itself. You don't even need to go outside. And if you just think about it, intuitively, you will feel that, yeah, this should be true. But if you try to prove it, you'll run into some trouble. I hope you run into some trouble because this gave me some trouble when I first learned this. Yeah, this is a very nice exercise, but let me give you a full proof. And yes, I encourage you to pause the video and try to find your own proof. That way, even if you don't figure out a proof, you appreciate this proof better. Once you try proving a lemma and fail, maybe, because you don't have infinite time, you appreciate the proof in the book or in a video much better. So let's see. So we want to show that there is some accumulation point of S sitting inside S. So we'll assume on the contrary, which means that we are assuming no point of S is an accumulation point of S. So therefore, for each x in S, there exist real numbers ax and bx such that this happens and this interval misses S entirely. The only thing it intersects S in is the point x. I'll explain. If this is the case, then no point of S is an accumulation point of S. So every point in S is isolated in S, right? That's what we just said in the previous slide. So you take an arbitrary, or you take any x in the set S, This has to be isolated in S under our assumption. So you should be able to find a neighborhood of X which intersects S only in X. Pictorially, you have the point X. All we are saying is you can find a neighborhood around it, or in fact an open interval around it, such that this open interval only intersects the set S in X. That is, that this is isolated in S. All right, but it is important to be able to argue that these things can be chosen to be rationals. Let me at least verbally argue it. So suppose you have found such AX and BX. Here is AX, there is BX. Once you found them, well, all you need to do is just find some rational number here and some rational number there, replace AX by that rational number and replace BX by that rational number. So you can, without loss of generality, or I don't know how to say it, you can find rational numbers AX and BX with the same property. And that's the key point of this argument. Okay? So we have that, and now define the map. And what is the best way to say it? So define a map F from S to Q square as Fx is Ax, and this is going to be very, very confusing. Oh my god. So here this was denoting an open interval, but here we are trying to denote an ordered pair. This is a very unfortunate clash of notation. This also denotes this open interval, while here in this line what we are trying to do is we are trying to say that Ax is the first coordinate of this value, and Bx is the second coordinate of this value. I hope you're not confused. Right, all we are saying is that to each x, we have found two rational numbers with a certain property. It's just that we are defining a map which identifies those two numbers. So to x, you just, the left end point you write as ax and the right end point bx, and that's it. So you have a well-defined map, and because of this thing, note that f is injective, right? Let me argue verbally at least. Why is it injective? So if it were not injective, then there would be two different points, x and x prime. Let's call it x and let's call the other one y. Suppose fx equals fy. That means ax equals ay. So here somewhere we have a, which is equal to both ax and ay. And by equals bx. Now by is going to be on the right of y, and by equals bx. Let's call that b. All right. And now this interval, which is, you can think of it as ax comma bx, or you can think of it as ay comma by. So this interval intersects S in two different points, both x and y. But that is contrary to the choice of ax and bx. Ax and bx intersect x only at one point, namely x. So this injectivity is not a hard thing to prove. It's just the main thing to observe, the whole reason why we are even constructing all these things. Now we have an uncountable set injecting into a countable set, and that is a contradiction. So that's a contradiction. And we are done. So we had assumed that there is nothing in S which is an accumulation point of S, but we ended up coming up with an injective function from an uncountable set to a countable set.